Complexity classes. P. The complexity class of decision problems that can be solved on a deterministic Turing machine in polynomial time. NP. The complexity class of decision problems that can be solved on a non-deterministic Turing machine in polynomial time. ZPP. The complexity class of decision problems that can be solved with zero error on a probabilistic Turing machine in polynomial time. RP. The complexity class of decision problems that can be solved with one-sided error on probabilistic Turing machine in polynomial time. BPP. The complexity class of decision problems that can be solved with two-sided error on a probabilistic Turing machine in polynomial time. BQP. The complexity class of decision problems that can be solved with two-sided error on a quantum Turing machine in polynomial time. Superpolynomial time. An algorithm is said to take superpolynomial time if t of n is not bounded above by any polynomial. It is omega of n to the power of c time for all constants c, where n is the input parameter, typically the number of bits in the input. For example, an algorithm that runs for 2n steps on an input of size n requires superpolynomial time. An algorithm that uses exponential resources is clearly superpolynomial, but some algorithms are only very weak superpolynomial. For example, the Adleman-Pomerantz-Rumeli primality test runs for n to the power of O log n time on n-bit inputs. This grows faster than any polynomial for large enough n, but the input size must become impractically large before it cannot be dominated by a polynomial with small degree. An algorithm that requires superpolynomial time lies outside the complexity class P. Cobham's thesis posts that these algorithms are impractical, and in many cases they are. Since the P versus NP problem is unresolved, no algorithm for an NP complete problem is currently known to run in polynomial time. Quasi-polynomial time. Quasi-polynomial time algorithms are algorithms which run slower than polynomial time, yet not so slow as to be exponential time. The worst case running time of a quasi-polynomial time algorithm is 2 to the power of O of log n to the power of c for some fixed c. The best known classical algorithm for integer factorization, the general number field sieve, which runs in time about 2 to the power of O to the power of n 1/3, is not quasi-polynomial since the running time cannot be expressed as 2 to the power of O to the power of log n to the power of c for some fixed c. If the constant c is the definition of a quasi-polynomial time algorithm is equal to 1, we get a polynomial time algorithm, and if it is less than 1, we get a sublinear time algorithm. Quasi-polynomial time algorithms typically arise in reductions from an NP hard problem to another problem. For example, one can take an instance of an NP hard problem, say 3 SAT, and convert it to an instance of another problem B. But the size of the instance becomes the complexity class QP and consists of all problems which have quasi-polynomial time algorithms. It can be defined in terms of D time as follows. Relation to NP complete problems. In complexity theory, the unsolved P versus NP problem asks if all problems in NP have polynomial time algorithms. All the best known algorithms for NP complete problems like 3 SAT, etc., take exponential time. Indeed, it is conjectured for many natural NP-complete problems that they do not have sub-exponential time algorithms. Here, sub-exponential time is taken to mean the second definition presented above. This conjecture for the K-SAT problem is known as the exponential time hypothesis. Since it is conjectured that NP-complete problems do not have quasi-polynomial time algorithms, some inapproximability results in the field of approximation algorithms make the assumption that NP-complete problems do not have quasi-polynomial time algorithms. Sub-exponential time. The term sub-exponential time is used to express that the running time of some algorithm may go faster than polynomial, but it is significantly smaller than an exponential. First definition. A problem is said to be sub-exponential time solvable if it can be solved in running times whose logarithms grow smaller than any given polynomial. More precisely, a problem is in sub-exponential time if for every epsilon greater than 0, there exists an algorithm which solves the problem in time O of 2n epsilon. The set of all such problems is the complexity class sub-exponential, which can be defined in terms of d time. Second definition. This definition allows larger running times than the first definition of sub-exponential time. An example of such a sub-exponential time algorithm is the best-known classical algorithm for integer factorization, the general number field sieve, which runs in time about 2 to the power of O to the power of n 1/3, where the length of the input is n. Note that it makes a difference whether the algorithm is allowed to be sub-exponential in the size of the instance, the number of vertices, or the number of edges. In parameterized complexity, this difference is made explicit by considering pairs. Exponential time hypothesis. The exponential time hypothesis, ETH, is that 3-SAT, the satisfiability problem of Boolean formulas in conjunctive normal form with at most 3 literals per clause and with n variables, cannot be solved in time 2 to the power of O to the power of n. The exponential time hypothesis implies P not equal to NP. Exponential time. An algorithm is said to be exponential time if T of n is upper bounded by 2 to the power of poly of n, where poly of n is some polynomial in n. Sometimes exponential time is used to refer to algorithms that have T of n equals 2 to the power of O of n, where the exponent is at most a linear function of n. This gives rise to the complexity class E. Double exponential time. An algorithm is said to be double exponential time if T of n is upper bounded by 2 to the power of 2 poly of n, where poly of n is some polynomial in n. Such algorithms belong to the complexity class 2exp time.